So I've been talking a lot about residuals, sums of squares, and sums of squares, and there are a few different types of sums of squares that we can compute, and you can look at the field text for the description in more detail. In short, the total sum of squares is the deviation between a score and the mean. The residual sum of squares is the deviation between a score and the line of best fit, or the regression line. And the model sum of squares is the reduction in sum of squares, the reduction in deviation between the total and the residual. R squared, also called the coefficient of determination, R squared is the coefficient of determination, and R squared indicates how much of the deviation in scores our model accounts for. It is an indicator of how well our model fits the data. Bigger numbers indicate that more data is accounted for. Bigger numbers indicate that more deviation has been reduced, that there has been a reduction in the amount of deviation from the mean to the line of best fit. Is the reduction in the sum of squared residuals reliable? Put another way, is the reduction in the sum of squared residuals more than would be expected by chance? Put even another way, is R squared from the same population as the mean? Oh, this sounds familiar, doesn't it? We use the F-test for our hypothesis test. R squared is an effect size, and the F-test is our hypothesis test. This is the formula for the F-test. A large F indicates that the R squared is not likely due to chance. In fact, the F-test is just like the t-test. And I believe squaring, if you take the square root of the F-test, you get a t. I believe you could check that out. It won't be on the test or anything, but just for your information. A large F indicates that the R squared is not likely due to chance. The coefficient of determination is not due to chance. What happens to F when there are lots of predictors? Take a look at the formula and think about what's going to happen to the size of F when there are lots of predictors. What happens to F when there are a lot of subjects, a lot of participants in the study? Take a look at the formula there. The F is adjusted and becomes smaller with lots of predictors, because with lots of predictors an effect is more likely due to chance. And the F becomes larger with lots of subject, because we have more confidence in our inferences from the sample to the population. The F-test is the test we use for the overall regression model, or the regression equation. Now, we can use a t-test to test if individual predictors or individual regression coefficients are significant. We use the t-test to test if individual regression coefficients, the b's, are significant. Similar to what we learned before, we're using the t-test to tell us if the regression coefficient is greater than 0. Is it greater than 0 given what we know about the variability of the data and our sample size? And I show you how you compute the degrees of freedom for your t. Regression and other tests. There we go. I can still see it now. Regression and other tests based on the linear model have assumptions. And we've talked about these assumptions before. Outliers can be especially troublesome and the text describes some diagnostic tests for detecting outliers. In my opinion, the easiest way of detecting possible outliers is just to look at a scatter plot of the data. So let's take a look at these scatter plots. Scatter plot 1 looks pretty good. This is how you want your data to look when you compute a regression. Okay, the line, you would imagine the line would go right through the middle there, and nothing is really too far away from where that line would be. What about scatter plot number 2? Scatter plot number 2. Does this scatter plot have an outlier? Yeah, it looks like the data point in the bottom right corner appears to be an outlier. It doesn't really fit with the rest of the observed data. Okay, all the other data is over here, and there's this weird case out here. How about scatter plot number 3, this one here? Does it have an outlier? Scatter plot 3 does appear to have an outlier here in the upper left quadrant, but given the rest of the data, you can see the data is spread out a little bit. Given the rest of the data, in this case, we may want to run an additional diagnostic test to see how bad this outlier actually is, especially in terms of its influence on the regression line. It looks like it may be pulling the regression line up a little bit on this side, but we could run a test and we could actually get a nice number to tell us, how big or how small of an outlier that is, and then we can decide whether or not we want to keep it. What about scatter plot number 4, this one up here? Well, I don't really think there are any outliers in scatter plot 4. Scatter plot 4 just looks like a case where there isn't really much of a relationship between x and y. But we could also run diagnostics just to be sure. I mean, maybe this one is kind of far away, but really it just looks like there's no relationship between x and y here, and yeah, nothing really to worry about. When we conduct a regression, we also want to make sure our residuals are normally distributed. Cross-validation is another way to test kind of how good a regression model is. With cross-validation, you have two sets of data, two data sets, and you calculate a regression equation for one data set, and then you see how well does that regression equation match on to the line of best fit that you get for another separate data set. So in a way, you're kind of you're comparing two different data sets to see is this line of best fit just for this sample, or does this kind of generalize? Is this more of something that we might find in the population? Is this generalized to the population? And cross-validation is one way of doing that. And Andy Field talks a little bit more about that in his chapter on regression. So in the field text, it's going to be important for you to review the assumptions of regression. Okay. These here show what's called Anscombe's quartet. They demonstrate how the same regression line, these are all the same line, these are the lines of best fit. They demonstrate how the same regression line can account for very different relationships, including relationships that are nonlinear, like these two. Regression is really only suitable for linear relationships. If interaction in regression is a case where the effect is nonlinear, it actually might look like this. For example, imagine a researcher wants to examine the performance of subjects with head injuries to the front and back of the head, and after taking a drug or a placebo. This is what we might call a 2-by-2 design. So 1/4 of people, one quarter of people have an injury to the front of the head, 1/4 have and take the drug, 1/4 have an injury to the back of the head and take the drug, and etc. It might be the case that the drug only has an effect in participants with an injury to the back of the head. There's no effect of the drug for participants with an injury to the front of the head. This is what's called an interaction. The effect of one variable depends on the presence or absence of another variable. Interactions are nonlinear, but we can create a new variable that is linear by centering the two variables, then multiplying them together and entering them into our regression equation. Notice x1 times x2 right here. That's the interaction term. Centering a variable is simply just subtracting the mean from each score, and so now the variable has a mean of 0. Don't worry too much about computing interactions, about the actual calculation. Just know what an interaction is. So we talked about regression, and that regression is only with continuous variables. Well, ANOVA is a special case of regression with categorical variables. Regression and ANOVA are actually the same thing and are types of what we call the general linear model, or GLM. In fact, you can think of ANOVA as a case of regression with dummy variables. Remember, I mentioned that before. ANOVA is also like a t-test with more than two conditions. ANOVA is a test of whether the means of the categorical variable are the same. Okay. Analysis of variance, ANOVA. Sums of squares are the same as the sum of squared residuals that we saw in regression. They're just computed slightly differently. And you can see the figure in the field text for an example. The idea is the same, but just take a look at the figure and you can see how they're just a little bit different. Again, we're looking at deviation. Okay, deviation from what our model predicts, deviation from the mean. Okay, we're comparing those two. The significance of an ANOVA is also evaluated using the f-test. We saw the f-test earlier for regression. The f-ratio is the average variation explained, in this case the mean of some squared errors, the mean sum of squared errors, divided by the average variance unexplained, the mean sum of squared errors of the residual. The f-ratio is an omnibus test. In other words, the f-ratio tells us if there is any difference in the group means, but it does not indicate where the difference in group means lies. So if you had 3 groups and you had a significant f, the distance could be between group 1 and 2, between group 2 and 3, between all 3 groups, between 3 and 1, etc. We evaluate the significance of the f-ratio based on the degrees of freedom and using an f-table. And Field talks a bit more about degrees of freedom and where the degrees of freedom come for the f-ratio in his chapter on ANOVA. We don't need to get into the specifics about what degrees of freedom are. Just know what the f-ratio is and kind of what it means, and maybe even know the difference between the f-ratio and the coefficient of determination. Post hoc tests are used after we find a significant f-ratio. We only use them if we find a significant f, and we use them to assess where the group means differ. Okay, so the f-test was the omnibus test. It tells us there is a difference somewhere, and we can use the post hoc tests to tell us where the difference is, between which groups. We can use a t-test to test the difference between 2 groups, and this is the most liberal test that we could do. However, when we compute a lot of t-tests, we inflate our type 1 error rate. That is, we're more likely to find an effect that looks significant but is really just a fluke. Another post hoc test that's commonly used is the Bonferroni test. The Bonferroni test is more conservative and is just the type 1 error rate divided by the number of comparisons that you're doing. In this way, with an increasing number of comparisons, it becomes more and more difficult to say that an effect is significant. There are lots of other post hoc tests, and they can have trade-offs in terms of type 1 and type 2 error rates. What's probably the most important thing to consider in terms of your post hoc test is the context of the test in the rest of the literature, and even better is to use theory beforehand to narrow down the number of comparisons that you calculate. Thanks.